To look at a Leetcode problem called lowest common ancestor of a binary search tree. So given a binary search tree, find the lowest common ancestor of two given nodes in the binary search tree. So basically we're given two nodes P and Q as the lowest node in T that has both P and Q, right? So we want to find the lowest parent, right? The lowest ancestor that both contains P and Q as the current node's descendants, right? So you can see we have a tree, and this is a binary search tree. So we have P and Q. The lowest common ancestor basically 6 because 6 contains 2 and 8 as its descendants, right? And you can see we have another example like this. We have 2 and 4. So the common ancestor can be the descendant itself, right? Or in this case, either P or Q, right? So you can see node 2 contains a child node of node 4, as well as it also contains the current node's node 2, which is equal to P. So this will be the ancestor for both P and Q, right? And we also have example 3. You can see we have P is 2, Q is 1. So the common ancestor is basically 2, right? So this question is really similar to the lowest common ancestor for a binary tree. So that problem, because that problem is not a binary search tree, so what we had to do is we have to do a post-word traversal to traverse the left, to traverse the right, to see if one side has a common has a descendant. If one side has a descendant and the other side doesn't, then that means that the left side has the lowest common ancestor, right? And if both sides has a descendant, then in this case, the current node is basically the ancestor, right? So in this case, what we can do for binary search tree is different. Is we can be able to solve this problem by using binary search, right? And the thing about binary search is that we can be able to control the range, right? So for example, what we can do is that we can use a pointers, right? Or sorry, in this case, we can just navigate based on the range. In this case, we have the range, right? The range is basically the smallest value between P and Q. And the max basically, or the right, is basically the maximum value between P and Q, right? So what we're going to do is that once we have our min and max, we're going to say while the root does not equal null, just like binary search, right? We get our current value. We check to see if current value is bigger than min and max. If it's bigger than the min and the max, right? So for example, if P is 2, Q is 4, right? And in this case, they're all smaller than the max, smaller than the current node's value. Then we had to search on the left side, right? If the P is 8 and then Q is 9, then we had to search on the right side because they're all bigger than the current node's value. So what we can do is we can be able to change the root, right? Change the current node's pointer. So root, if it's all bigger than, if the min and the max are all less than the current node's value, then we can just search on the left side. If P and Q, they're all bigger than the current root's value or the current node's value, we can just search on the right side. We just get root is equal to root not right. If we have a situation, right, where current node's value is equal to min, or current node's value is equal to the max, or if we have a situation where current node's value is between min and max, then we can just break and return the root, right? So we're basically just performing our binary search and trying to solve this problem, trying to find the lowest common ancestor, right? And you can see that for this algorithm, the time complexity is basically big O of log n, right? Because we're we're basically using binary search to search. So the time complexity is log n, and the space complexity in this case is basically constant, right? So we're just using pointers or just pointer to manipulate, right? So we're using the root pointer to control which side we want to search, right? So there you have it, and thank you for watching.